streaming, get this show on the road. So we have this 1 degree of freedom system, and I guess that echo. We even have homework. We have like locations of all the hinges, like where they are. We know how fast our crank arm is moving, so that link 1 is our crank arm. So let's draw this out. Not screen key. I want. Oh no. I don't want screen key. Screen grab. So R0, like location of hinge 0, is right here at our origin. And then RA, we move backward, like move negative X, but up Y. So somewhere like right in here. Oh my God, the X input. Just. No, I need 12 and 10. Here we go. It's not letting me draw. Let me draw. Move it down here. So A is somewhere up here, and we have a link going from O to A. Then B, move 1/2 over, 0.8 up, so something like this. And then C is 1 meter to the right and 0 up. And then I'll draw the angles of like everything on there. This is theta 1, that's our theta 2, and this is theta 3. So angles are kind of weird, right? Like depending on where you say a 0 angle is, it'll change. You could use the y-axis and say it's something else. We could have used theta 3 pointing the other direction. It's nice to always use like x-axis location, like what is the angle from the x-axis, and again, like counterclockwise positive angle. That way your location is always a cosine theta and a sine theta. Cosine's always your x component, sine is always y component. Again, you can do it however you want, but that's just, it's a nice format that kind of keeps track of a lot of the bookkeeping. All right, we know there's 1 degree of freedom. At least I think we know that. We talked about it on Wednesday. Maybe you haven't like accepted it in your soul of like, you're still grappling with this idea of a degree of freedom. But if you put that like philosophical discussion aside and you say, yes, there's 1 degree of freedom, that means if I have angle 1, there should be an equation to find angle 2 and angle 3. There's nothing, like everything should be solvable in terms of that one angle, or vice versa. If I have 3, I could find 2 and 1, but somehow if we have one constraint, we should be able to find everything else. How on earth would we do that? What do you think? What would we do for that? I want you to just like think about it and like ask somebody else, like try some brainstorming here, because we want to figure out what are the constraints on this motion that are describing how theta 1, theta 2, and theta 3 are all connected. Same kind of remember last time we talked about like how many equations we needed to solve for how many unknowns? Same thing here, same rules apply. Think about it, talk about it. What do you think? Okay, what about it? The lengths? Okay. What does that do? Okay. Yeah. So because that's a fixed position. No? Okay. Well, we know the lengths of everything, right? So we know it's like a parallel ring. Or not parallel. We know that it's a polygon? What's that? Yeah. What is that? Quadrilateral? Sure. Quadrilateral doesn't have to be parallel, right? So we know it's quadrilateral. How do you find this stuff?
Set them off, get solved from there.
Equilibrium?
I think so.
You can find oh, you think
starting
forces, the kinetics will define it?
possibly. Unless it's one of those 3 bodies thing where you can't predict the route it's going to.
No,
They're all linkage.
there's no chaos theory here. This is all like, we're good.
Well, they are stabilized. They're all independent with the answer direction. I was looking at this and I was like, there's only so many degrees it varies. Yeah.
Okay. Yeah, or the triangle. Okay. Right, you think right triangles, I guess, somewhere in there.
Just straight dizziness.
If you look at it, why you said it is close and closer to there, we know the length is just straight.
Well, what if we only know one?
Well, we know the lengths.
Chris, I lost when I was
A to B.
that's why I was like banging my head against the sliding door. Because I was like, I literally lost his IG on his written end. I went uphill on the bike. I was so excited to have the bike. I didn't realize that it must have vibrated out of my pocket while I was coming down. But then when I realized I was missing a wall, I was like, I'm going around uphill. Missing. Justin's buddy Dylan had, in the 3 minutes I was gone, found it, picked it up, and moved it. Where did he move it? Don't know. He told Justin at 1:30 in the morning, which is exactly when I lost it. Oh, so he literally found it moments after I dropped it. Okay, that's lucky. Okay, at least he has it. He's probably laughing about it, honestly. He was.
Yeah, so how would you, what would be the connecting sometimes it then you introduce more angles that you're trying to solve for, like more triangles. You split it up into. Okay, so the angles, so we know those internal angles have to add up to 360 degrees. Yeah, that gives us like one equation with two unknowns. Did anybody else? I didn't want to like jump ahead if anybody else had. Yeah. Absolutely. Yeah. Yeah. Because even like right now, let's say this one is 135 degrees. It could either go up and down, or it could come down and then back up. It's kinematically like locked into that. It's not gonna like jam itself into the other position. Like once it's kind of set up, it's gonna be there. But there's definitely more than one solution. That usually happens with like big rotations like this. And that's where dynamics gets like weird and fun, is that everything rotates so much, and rotations create nonlinear properties, like your kinematics and your dynamics. So it's more fun, but also sometimes you're like, can't you just be linear for once? All right, so let's try this. What do we think? Blue vectors? All right, blue vectors. Here, so this is a process. It'll work for like 99% of like kinematic descriptions. So there was talk of like, okay, we can divide this up into triangles. We know positions have to do with sines and cosines. This is one way to kind of like formalize that into what we already know how to do. So I'm going to draw what is that bottom, so when I go O to A, what is that vector? What is that describing? Position of what? A, with respect to O. So this is RAO. AO. And then this is the next one up, kind of going along this loop. What is this vector? What's it pointing at? AB, yeah, it is, it's AB, but this one's the position of B with respect to A. There's just like a negative, whether it's positive or negative. So BA. And then what about going from B to C? What is that one? CB, yep. C/B. And then what is that last one at the bottom? OC, yeah, CO, or OC, yeah. So position of O with respect to C. I'm gonna call it R negative RCO, just because that's the way I think about things. And we have RC described already as a +1. If I add up, let's write it out. RAO plus RBA plus RCB plus, well, let's do negative, minus RCO. What does that equal to? 0? My wife, we met in engineering classes. Now she's a physician assistant, and she dropped because she never wanted to deal with a vector ever again. And just decided like, oh, let me do something easy like healthcare, which is so much harder than engineering work. And she's like way smarter than me, but she never wanted to deal with vectors again. But anyway, so the thing that she always said about engineering classes and math was like, it's always 0 or infinity. Like, I don't understand why you need so many proofs if everything's just going to be 0 or infinity. Yeah. Yeah, we just did a big circle, right? And if you end up back where you started, it's 0. So if I add up those 4 vectors, I made a vector loop, and it's back to 0. And you can do that for any kind of constrained system like this. If you have rigid bodies with connections and this kind of thing, there's always some kind of relationship where maybe it adds up to 0, or maybe it adds up to like a constant value or something. There's usually something like that. How many equations does a vector equation give you? Like if you say this vector equals that vector, how many does that give us? Does that question make sense too? Yeah, it depends on the dimensions. But here, in this case, we have 2-dimensional vectors, so we have 2 equations, and we have 2 unknowns. So this should be, there's math involved, like we got to do math next, but at least conceptually, we've solved the kinematic constraint problem. We know that theta 1, 2, and 3 have to be connected by 2 equations. We created a vector equation where that is true. Makes sense? That's cool. So then, does this tell us anything about velocity? Like the velocity of A and the velocity of B with respect to A, the velocity of C with respect to B. No? Nothing? What is it? You don't think so? Okay.
These are vectors, right?
We're using vectors, yep. Maybe?
We're given dx and dy.
Yep.
We know dy is 0, so we can sum up the vectors so that they're 0. We can separate them individually and see which each part would go if they weren't connected.
Okay. Yeah. Take a derivative? What does that look like if I take the derivative of 4 vectors? Partials. R goes to V, take the derivatives. Thanks, Jimmy. Yeah, nice. Take the derivative. Get to the chopper. So I just take this whole thing and say the derivative of this. What's the derivative of the position of A? Time derivative. That one, it sounds like a trick question. Because it's like, I don't know what A was. Yeah. It's velocity. Yeah, it's VA. Like that is the velocity of A. So if I take a derivative, I just defined the velocity of A. And yeah, like maybe the actual equations will take some partial differential stuff, like maybe there's some other things that I have to do, but it's directly in there. Like if I know position and how it's related to other positions, I also know how all the velocities are related. Same thing here. This relative velocity, this relative, oh, my bad, V of CB. What about that last term, RCO? Do we know anything about that velocity? A 0? It's always 0 or infinity, right? It's always the answer. Why is it 0? Why is RCO, derivative of RCO 0? It doesn't change. It's describing the location of 2 points that can't move and their relative position. So their relative velocity is always 0. They always have to be like, so minus 0 equals 0. Nice. This works every time, like no matter how the 4-bar linkage is set up. It even works for like a 5 or 6-bar linkage. It doesn't give you as many constraints, like you're still just getting those 2 constraints, but it works. And now you're an expert in kinematics of rigid body systems. So now let's do the hard part of like actually plugging in what these terms are. So L1 is our magnitude, like it has to be L1 away. What's the direction? Where is it going? Sine theta 1. We definitely need a sine theta 1. Is that in our x direction or y direction? Y direction. What about for x direction? How far is it along the x direction? I know it's going like negative, and you're trying to figure out quadrant 2, what's the, is it 180 minus theta, is it theta? Yeah. Here, that would give us a positive x value. So we could say negative cosine theta minus 180, or we can just say it's cosine theta 1 along that I direction. But in like you're doing the right math, like you're kind of thinking about it in the right way of like if theta is more than 90, then this magnitude is actually cosine of theta minus that. But the nice part of like if you always define x-axis as your 0 angle, cosine theta is always described, no matter which quadrant you're in, cosine theta describes positive and negative location. So we're good to go. It works pretty well. There's a method to the madness of like why choose these kind of things. Bless you. I know the magnitude of RBA has to be that 1 meter. What's the direction? Where is it going? It looks the same? Yeah, it's the same, like same pattern. Like we say that it's cosine theta 2 along the I, sine theta 2 along the J. So I can do, and again, the way that my mind thinks, I'm going to say RBC, just flip that vector because it's the same but negative. Just the way that I like to do things, so that I can say L3 cosine theta 3 along the I, sine theta 3 along that J. All right, so here is the part where people usually get a little tripped up, but we can fake it. We'll talk about it. And once we do it once, we see the same pattern is there. Like once we do this derivative once, we can kind of apply the same pattern over and over. So I want to find velocity of A in terms of L1 and theta 1. Kind of makes sense, because what I want to do is figure out how fast theta 2 and theta 2 and theta 3 are changing. So I need that VA, VB, like I need all those velocity components. What is this derivative? How do you do this derivative? Try it out. We'll give like, not like time, if you don't finish in 30 seconds, there's no penalty, but try like 30 seconds, give it a shot. I want to see what you come up with taking time derivative of a cosine theta and a sine theta, two vector components. Confused? No? Not worth it. Yeah, yeah. I mean, once you have theta 2 dot, like the rate of rotation is the rate of rotation in any coordinate. Oh, yeah. Yeah, so we're defining theta 2 dot. Like right now we're defining theta as like disk angles, but what we want to find is how fast it's spinning around there. Yeah. So it's a couple of like abstracts to get to a very concrete answer. So like this is how fast that part is spinning. Okay, Jimmy has an answer over there.
We're trying to how to simplify this.
Yeah.
We're trying to figure out if there's going to be.
I mean, they're like perpendicular components, right? So you can't add them together.
Yeah.
So it's okay to leave them separate. Here's my I, here's my J.
Okay.
Yeah, it's not like you need like the sine squared plus cosine squared.
Yeah, that's right. Yeah, we have
Derivatives. Anything? Negative sine. Alright. We have a hint up on the board. The chain rule. The chain rule. What is the chain? How is the chain rule applied here? What is Jimmy talking about? What? No.
Well, the problem is that L1 is probably a constant, right?
L1's constant, so we can pull that one out.
So we can pull that one out, and that's not going to affect it. So it's just cosine of theta 1 I plus sine of theta 1 j.
Yep.
And then I think we can ignore I and j for now. Well,
Those are similar to constants, right? Like it's just telling you a direction.
Yeah.
Like it's.
So we can just focus on theta. So it would just be the derivative of cosine theta 1 plus sine theta 1 plus cosine theta 1 plus the derivative of sine theta 1. Is that it? Yeah.
All times L1. Okay. So do we need chain rule?
I think chain rule is only for like multiplication.
For multiplication? So no chain rule. No chain rule. Yes, chain rule? Yeah, I think are you thinking of chain rule? Or wait, did I do that wrong? Is this like the chain rule that you're thinking of? Derivative of u times v is derivative u times v plus, yeah. That's one of the chain rules. This is one version. Another one is like if I'm trying to take the derivative of f of x, my function is not a function of time, it's a function of x. Yeah, that one is the product rule. Yeah, thanks. Product rule. There we go. Yeah, I'm like, that's product rule. I think product rule is kind of an application.
It would be more like if you had like a cosine of like 2x.
Yep.
That'd be but what if the equation is not that?
Yeah, and so that's what we're dealing with here, because theta is a function of time. Like theta is changing over time, so there's got to be something that relates theta to time. So I can't say the derivative of time of sine theta is negative cosine theta. I also need to take derivative of that. So what we would say is that it's dx dt times d dx of f of x. So this becomes like df dx times like an x dot, something like that. So we can do the same thing for this function. And I guess all that is like my notes. So we end up with the speed of the thing is position times rate of rotation. And that kind of makes sense. Like if you're rotating at a given rate, the farther away you are from the point of rotation, the faster you're moving. And if L is 0, if you're standing on the origin, you don't need to move at all to rotate at 10 radians per second. And then the direction is kind of 90 degrees to what we found before. We just turn the sines to cosines.
So how can you take a derivative with respect to time if there's no time variable in the equation?
Oh, because we don't know what theta, like theta doesn't have a time in there. So So the assumption is like if we like thermodynamics, you talk about like the state of steam, like what are the properties that describe that steam. In dynamics, when we talk about the state of an object, we're saying what is its position and what is its orientation. That kind of describes this, because it tells you everything you need to know. Like if it changes temperature, it doesn't change where it is, at least in a dynamic sense. And we're not really considering like thermal contraction, thermal expansion, or anything like that. So everything in a state is some function of time. Like there is, if time changes, that state could change. maybe it's a constant, but it's still some function of time. So that's why when we take a derivative of position, all the things that describe the state of where that is, they have to be considered some function of time. There are cases where we can say it's equal to 0, like in the case of those two fixed O and C points, but in general, we do have to say, like, there is some, I don't know what the function is yet, like I'm trying to figure that out, but I know that it's a function of time. That part's weird for a lot of people. Like, in order to get to the equation to solve for theta dot, you need to create abstract equations where theta dot is just like a variable. It is changing. We know that it's changing, and we're trying to figure out how it's related. Yeah. Long answer to a quick question of like, yeah, where'd that dot come from? Okay, so then we also have like VBC is L2 times theta 2 dot, and it's the same form, right? Theta 2 along the I, cosine theta 2 along that J, V of, what else do we need? Oh yeah, V of B slash C. That one's L3. Whoops. This is BA. I was trying to go quick because I realized we're like almost out of time. So with vector, since we have, I'm going to scroll up and then back down so I can write out the vector rule. We had this vector equation, like VA, VBA, VCB, all add up to 0. So I can write all that out. So the I components all add up to like L1 theta 1 dot, sine theta 1 plus L2 theta 2 sine theta 2 equals L3 theta 3 dot, sine theta 3, L2 theta 2 dot, cosine theta, that should be a 1, L2 theta 2 dot, equals L3 theta 3 dot, cosine theta 3. So we have these like equations. We have two equations with really two unknowns that we know theta 1 dot, and we don't know theta 2 dot, theta 3 dot. What about like the actual angles, theta 1, theta 2, and theta 3? Do we know those? Again, I'm going to scroll up and then we'll come back down. I'm going to copy something. like if I know where hinge A is, do I know what theta 1 is? Or could that be different? Is there more than one value for it? Well, yeah, there's definitely more than one, but can you change the angle and the position independently? Oh, yeah, the equation did add up to 0, but I flipped the sign on, so Jimmy's asking about like the I and J. I added everything up to 0, but I just brought over one of the terms. I brought over my my VC, my negative VC. I brought it over to the other side. So like here, this RA is defining the sines and cosines. Kind of like that. Or sorry, it's L1 times that. My bad. Again, I'm rushing a little bit. So if I take negative 0.203 divide by L, that is cosine theta. And if I take 0.1459 divide by L, that is sine theta. Sine theta 1, sorry, sine theta 1. So really, like I can do like the trig to figure out what is theta 1 and then plug it back into sines and cosines. But really, at the end of the day, I need sine and cosine to plug into my equations anyway. So I could shortcut if I want. Oh, we're over time. Sorry. And then Monday is the career fair. Is everyone going? Monday's like STEM career fair. We're going, yeah, the plan was build quiz 1 on Monday, but I definitely want you to go to the career fair. So, I don't know. Definitely go to the career fair. Think about, like, especially in this class, like you're building some pretty specific skills in dynamics that not many people have. Like even other engineers struggle with dynamics. You're thinking deeply about it right now. You can add that to your resume. If you need help with that, like Monday, you could always ask before you go to career fair. You could stop by my office or send an email over the weekend, and I'll try to get back by Monday. But anyway, definitely focus on your career. Like how does this fit into what you're trying to do? And yeah, have a great weekend. Thanks a lot. And then for the stream, I do want to finish. I wanted to finish what we were working on, but I'll do that maybe like Monday morning. I'll finish out like what we were working through today, so we have a record of where we were going with this process. And then I'll show like kind of how I solve 2 equations, 2 unknowns. Okay, thanks for joining, and I'll catch you next time.